Okay, thanks.
Nice, nice.
Uh,
Okay, great. But does the camera record or no?
it should just record what's on the screen at the moment.
Well, I put my slides on my webpage, so that would help. And I figured if there were people on the Zoom who had a laggy connection, then they could just go to the webpage and find it. But I wrote the URL on the board, so if you're on the Zoom, you can just Google David White Dennison, and you'll find the slides. Yeah, and so I want to start with an old problem from 1995 that goes back to Baez and Dolan. So they were working on trying to come up with a higher categorical model for n-dimensional topological quantum field theories. And at the time, they proposed that weak n category should be a good model, but there was no accepted definition of weak n category. But still, they figured based on this kind of motivation, there should be some relationships between categories of weak n categories as n varies. And any good model for weak n categories should satisfy these relations. So then subsequently, many definitions came about. Charles Resk has a definition, Tom Samani, Simpson came up with his higher Siegel categories that are in his book. Dimitri Ara, Bergner and Resk had multiple different models. So now there's sort of too many models of weak n categories, and it's an active area of mathematics. So I'm going to be talking to you about the Baez-Dolan stabilization hypothesis, which I'll state on the next slide, and I'm going to show you a proof of it, omitting some details. This is all joint work with Michael Baton, and the paper that I'm talking about is already on arXiv. I have at the end references, but it's a paper the only paper that I have that has the word substitutes in the title, and so it goes through this proof in more detail. The paper is about 80 pages, and then there's another paper which is like 30 more, so it's a lot of stuff, so I'll skip a few details. But the point is, our proof is actually gonna hold in all of these models, and that's something pretty nice, we think. So throughout the talk, let SPK be k-truncated spaces, so these things model k-types. And for example, Resk's model of weak n categories is theta n of SPK. So this models n plus k comma n categories, which I'm going to define on the next slide, which means that n cat is kind of, we get at it this way. So we're going to need these truncations throughout the talk, because first of all, they come up in the definition of Resk's model, and then later for all these other models, we'll be doing some truncations of them as well. Okay, so let's try to state the stabilization hypothesis. Suppose you have an n category, which means you have some objects, some morphisms, two morphisms, etc., up to n morphisms, and you want to reindex it to an n-1 category. So let's suppose that this n category has only one object, so that reindexing, I don't lose too much information. Well, when I do that, my new objects are going to have extra structure because they also have a composition law, because secretly my new objects are the old morphisms. And my morphisms are going to have two composition laws, vertical and horizontal composition. So this is some extra structure of what I get. So for example, if I start with let's say a 2 category that has only one object and only one morphism, okay? And I'm going to reindex twice. So I go from the 2 morphisms to the objects. Well, then the collection of 2 morphisms had previously a vertical composition law and a horizontal composition law. So my objects now have 2 commuting multiplications that work in a nice way. And so by the Ekman-Hilton argument that topologists learn in first year algebraic topology, that means that I get a commutative monoid structure because I have 2 commuting multiplications. That's extra structure. Now you can ask yourself, what happens if I go from, say, a 3 category that only has, one object, one morphism, and one 2 morphism, and I go all the way down to a 0 category, just to the objects? Then I would have 3 commuting multiplications. Is that even better structure? And the answer is no. If you have 3 commuting multiplications, you still just have a commutative monoid. The 3 multiplications are all the same. If you go from a 4 category to a 1 category, or maybe I should have said a 0 category, 3 cat to 0 cat, no extra structure. From 4 cat to 0 cat, same thing. You could have 4 commuting multiplications, still just a commutative monoid. So this reindexing thing stabilized after a while. You can also ask yourself, what if I go from, say, a 3 category to a 1 category, or from a 4 category to a 1 category? I should be getting some extra structure there on both the objects and on the morphisms. So this table appeared in the paper by Baez and Dolan, and it shows that this stabilization is happening. If I go from a n plus k, so a 2 category to a 0 category, I get a commutative monoid. Going from a 3 category to a 0 category, I get still a commutative monoid. If I go from a 2 category, so 1 plus 1, 2 category, to a 1 category, I get a monoidal category because it has that extra structure. If I go from a 3 category to a 1 category, it's braided monoidal. And from a 4 category to a 1 category, it's symmetric monoidal. And after that, there's no extra structure from higher. And the same phenomenon going to 2 categories. So there's this sort of line that it seems to stabilize after that line. So they essentially made a hypothesis that any good definition of weak n category should satisfy this. And let's try to state it a little bit more formally. So we're going to say, suppose we start with an n plus k category that's trivial up to k, meaning 1 object, 1 morphism, 1, 2 morphism, so that we can do this reindexing thing. Then when we reindex k times, we're going to have an n category with this extra structure that comes from reindexing k times. So let's denote by n cat sub k the collection of n categories with the extra structure that comes from reindexing k times. Of course, there's a forgetful functor. If I reindex k times versus k minus 1 times, I can just kind of forget that extra structure that I got from that extra 1 reindexing. And it happens to have a left adjoint called suspension. This is defined in the Byers-Dolan paper. So their hypothesis is that beyond that line that I drew on the previous slide, that it should be the case that the suspension functor is an equivalence in a suitable sense. Now, it's not going to be like a fancy, strict equivalence of categories. Actually, when they made this hypothesis, there wasn't even a definition of n categories, weak n categories. So being a homotopy theorist, I interpret this to mean equivalent equivalence in a suitable sense, or some equivalence up to homotopy that we have to define. That's the hypothesis. And Michael Baton, my co-author, had been working on this project for many years. For one thing, he realized that the extra structure that you get on one of these categories, these things are called k-tuply monoidal weak n categories, because it has the structure of k extra multiplications that you got from forgetting the k levels. So the structure you have on a k-tuply monoidal n category is an algebra over something called a k-operand that he invented. That's how he recognized this extra structure. So I'm going to define k-operands in a moment. But before I do that, I'll state the stabilization hypothesis formally. And so the stabilization hypothesis is that if I can encode this extra structure by a k-operand, that's from forgetting k levels, and I can encode also from forgetting k plus 1 levels, then in the stable range below that line, that this will be equivalent equivalence between forgetting from k levels and forgetting k plus 1 levels. And actually, Michael proved this in 2017 in a paper in the Proceedings of the AMS. But we're going to prove something stronger. We're going to actually have a equivalent equivalence of categories of k operands and k plus 1 operands. And this is going to, as a special case, we'll be able to deduce the kind of weaker form of Byers-Dolan stabilization. So our goal in this talk is going to be to make sense of all these symbols and to prove that this category here of n cap, so the category of k operands, which I'll define on the next slide, is equivalent to the category of k plus 1 operands in n categories after a suitable localization. And in fact, this is going to involve comparison to the category of symmetric operands. So SO is the traditional symmetric operands. Getting back and forth between a k-operand and a symmetric operand is something Michael Baton knew how to do for a long time. And so we'll sort of get this equivalent equivalence as a special case of like a 2 out of 3 thing. So if we can make a good comparison to symmetric operands, we'll be happy. So I'll define all these symbols. I just wanted to write on the board what we're aiming for. And we're going to do this in a great deal of generality. When I write ncat, that's some nice model of weak n categories, and it should in particular apply to all of the models that I wrote before. So for all of these models. So when I write weak n category, I mean any model like this. So we'll do this all in the setting of some general V. This will be like some general V, which is going to be a nice monoidal model category with some properties. But those properties will be satisfied by all those examples. Okay. So I'm going to go a bit quickly through this here, and that's one of the reasons I put my slides online so people could kind of look at that if they wanted to. But the category of k operands is going to be defined by starting from k ordinals, just like the category of symmetric operands is defined starting from symmetric collections. And then you transfer from, so a symmetric collection is like, one space for every n with the action of the symmetric group. And here what we're going to have is like one object for every k ordinal. So a k ordinal is just a finite set that has k binary relations satisfying some properties, which you can also write in a tree way. And these k binary relations should be thought of as kind of, they're going to encode the k multiplications, the extra multiplications that I have. When I take presheaves on this, that's where those things are headed. So that's what a k ordinal is. It's just a finite set with k binary relations, and I'm going to take presheaves on these things. So I think we denote by q sub k the category of, q sub k is the category of k ordinals. And then, like I said, I'm taking some v, which is my model for n categories here. I'll put a v here. But in practice, this v is going to be like that. And I'm going to take presheaves from this category of k ordinals into v. That's the idea. And then I'm going to transfer up from that thing to the category of k operands, just like you would transfer from symmetric collections to symmetric operands. So maybe I can even write that here. You have, from the symmetric groups into v, and you transfer from there up to symmetric operands. So you've got some transfer picture like this. This is qk plus 1 because I want k plus 1 ordinals. If I want to do k plus 1 commuting multiplications, I need k plus 1 binary relations. Okay. So what is a k operand? I mean, it's a presheaf like this with a unit axiom and a composition law and associativity and the sort of the usual stuff that you would expect from the theory of operands. It's not super important what these this form. You don't need to understand the definition at this level because our work is at a much higher level, which is substitutes. That's coming. Okay, so that's what a k operand is. It's like a generalization of an operand that somehow has k nice commuted multiplications. And then this qk that I just wrote here is the category of quasi-bijection. So I take the k ordinals. Remember, that's a finite set with k commuting k nice binary relations. And I look at the category where the maps are bijections in there. Now, this thing, so I have this category of collections. This is like the analog of symmetric collections. These are the k operands. I have a forgetful functor, and there's a free functor going back. So it works just like symmetric operands. What's different from symmetric operands is that this category of, like k ordinals with quasi-bijections acts on the category of k operands, but not invertibly. And that's a big difference from the case of symmetric operands. In symmetric operands, this thing is a groupoid that acts invertibly, but now we have like a category of unary operations, and they don't act invertibly. So this is something different from the theory of operands, and that's why we're going to need substitutes to encode that. So we'll get there. But I just want to tell you a bit more about this mysterious qk. So just like the category of all symmetric, this groupoid of symmetric groups is a coproduct of all the symmetric groups, one for every n. Similarly, this qk is built from these qk sub m's. I'm going to show it in a second. I just mentioned that these things are like the unary operations. It's not a groupoid, so we can't use Feynman categories or colored operands. But I meant to write something else about this qk. I'll write about it in a second. I'll tell you more about this object in a second. But basically, the point is this is like categories of collections, one for every level n. And our idea here, this loc that I wrote on the board, is going to be, let's localize to actually force this thing to act invertibly up to homotopy. So it doesn't act invertibly, but I can do some kind of left mouse field localization, we'll get there, to make it act invertibly. Why would I do it? Here's the motivation. So if it exists, right now we don't even know that there's any kind of homotopy theory here, no model structure, nothing, but if it exists, then this, this localization, we're going to call the elements of this category locally constant k operands, by which I mean the Feynman objects in this model category for those who are experts. And locally constant k operands are actually higher braided operands. That's a paper Michael Batanin wrote back in 2010. So why would there be any connection to higher braided operands? The answer is, I'll give you 5 reasons why. So these locally constant k operands, where I force this thing to act invertibly, if I take k equals 1, I get the homotopy category of non-symmetric operands. If I take k equals 2, I get the homotopy category of braided operads, and at k equals infinity, I get symmetric operads. So that's weird. I'm getting 3 flavors of operads out of this general machinery, and there should be something kind of between braided and symmetric, and that should be higher braided with some additional structure coming here, which comes between 2 and infinity. Furthermore, in each of these 3 settings, the contractible operads, contractible cofibrant operads, I should have written, detect loop spaces. So for non-symmetric operads, contractible cofibrant operads are like A infinity things. They detect 1-fold loop spaces. For braided operads, you detect 2-fold loop spaces. And it's a famous theorem, I think, of Peter May, that for symmetric operads, you have infinite loop space machine for these E infinity operads. So what's cool is that for these higher braided operads, if you take the cofibrant replacement of the terminal thing, which is how you define, say, one way to define E infinity operads here, or E2 operads there, you get En operads, and they detect n-fold loop spaces. So that's another argument that these locally constant K operads are a good idea because they're sitting between the stuff that we already know, but at all levels n. I promised before I would tell you a bit about this QK, that the QK category of collections is built on these things. They are homotopy equivalent to unordered configuration spaces of points. So that generalizes the situation for non-symmetric, braided, and symmetric as well. And actually, our proof of the stabilization theorem is going to come down to an analysis of these types of configuration points. And then I think this is the last reason. The fundamental group, if I take fundamental groupoid in each of these cases, the fundamental groupoid of the higher braided operad for k equals infinity gives me symmetric groups. For k equals 2, it gives me braid groups, and for k equals 1, it's contractible, and that's sort of the indexing thing for non-symmetric operads. So I'm really getting these 3 flavors in a strong way as a special case out of this general machine. There's also a comparison between QK and sigma, and that comparison is going to be used heavily right here to get equivalence here, then I'm going to lift to equivalent equivalence there. But we'll get to that. But it's only an isomorphism on homotopy groups less than or equal to k, hence the need to truncate. That's what the localization, when I write loc here, we're going to be doing the localization to make it so that this is actually giving me equivalent equivalence that I can. All right. Okay, so far, we've talked about the bias-Dolan stabilization hypothesis. We've defined past K operads. I mentioned this idea to do localization. So hopefully, if you saw this, you might think, well, that sounds like a good idea. It's got all this benefit. But to do that, we have to put a homotopy theory here, or else what are we talking about with this? We're going to homotopically invert so that this QK acts invertibly. So I better tell you how to put a homotopy theory here. So the way that we're going to encode this category, we can't encode, this lifting here is not encoded from a colored operad or a Feynman category because of this issue about QK not acting invertibly. I can make it act homotopically invertibly later when I do the localization, but just to even at the level of categories, this transfer is not a colored operad of any kind. So you have to have some fancier way to encode algebraic structure, and the fancier way is called a substitute. So these go back to Day and Street, to this, some old school category theory. The idea is that a substitute is that P is something like an operad, and A is like its category of unary operations, but not a groupoid of unary operations. So just like an operad, there's some way to sort of multiply things together, and it has a unit thing and a composition thing and equivariance isomorphisms for some sigma group actions. The way I think about it, and this is correct, is that it's a colored operad together with a functor, an enriched functor, but a functor, from A, this extra data, to the collection of unary operations. In other words, this A thing is a category of unary operations. And in fact, well, the main example is going to be that P will be giving us K operads, and the A part will be this category of quasi-bijections here. But these things were actually invented a couple of times. Getzler called them regular patterns, and Peterson called them category-colored operads. So that's really how I think about them. It's like a colored operad, but with a category of colors instead of a set of colors. So we won't, again, need this level of detail for the purposes of today, because I'm just trying to give you a roadmap to this giant paper. Instead, the main point is that if I could transfer a homotopy theory to a category of algebras over a substitute, then that would in particular give me a homotopy theory here before localization just on the category of K operads. And also as a special case, it would give on the category of symmetric operads. This one we knew how to do without this machinery of substitutes, but it comes out from the substitute machine as well. Okay. So how do you transfer a homotopy theory to a category of algebras? Suppose you have a monad on a cofibrantly generated model category, and you want to transfer a model structure to the category of T algebras. Well, the thing you have to always do in this case is if somebody gives you a generating trivial cofibration in the model category, you have to be able to analyze a push out of T algebras where I take the free T algebra functor on that generating trivial cofibration and take a push out in the category of T algebras. And I have to prove that maps like this on the bottom are weak equivalences, and also transfinite compositions of pushouts of these maps are weak equivalences. This is the usual machine for transferring a model structure. If you can do that, then there's this general lemma that's been proven many times in the literature, tells you that the category of T algebras has a transferred model structure. If you can only do this analysis when you have a cofibrant T algebra here, then you only get what's called a semi-model structure. And in the case of substitutes, that's what's going to happen. We're going to end up with semi-model structures on everything in sight. To get full model structures, we require strong hypotheses on V, and that would rule out the examples we had in mind. For experts on operad theory, there are many ways to do this with operads. Like there's the Berger-Mordijk conditions, where if you have a fancy interval object, you can get a model structure you can analyze as pushout. But in these categories we care about, you don't have that. So you can't use the Berger-Mordijk approach. You have to analyze this pushout another way. And that's what most of my work has been about in my career, doing this for operads and colored operads and various other ways of encoding algebraic structure. So it made sense to do it for substitutes as well. So I will tell you in a moment what semi-model categories are. For the moment, we don't need them because we're going to talk about localization first. So the point is, we're going to use some technology like this to put a model structure on K operads.
Where do you transfer the model structure from the pre-sheet category?
From the pre-sheet category. So this thing always has the projective model structure. No problem.
What is V?
V is going to be a monodal model category. Yeah.
And why is the problem with the cofibrant object if you can just take the injective? I mean, you could take the injective instead, right?
The injective model structure here.
Yeah.
So then, okay, that's a good question. Let's see. So you would have to, so no matter what, you're going to have to prove this fact here for generating trivial cofibrations. So in the injective model structure, the generating trivial cofibrations are a lot more difficult to understand. So you would have trouble even getting the game started. The projective is going to be a better model structure. However, in our theorem, we actually prove that we do get transfer principles for both the projective and the ready. I have to check if we do it for the injective. I think we do for the injective as well, the general theorem. But
That makes sense.
yeah. Okay. So the good news is that we're going to do this, and we're going to get a model structure on the category of K operads in V, where V could be, for example, Resk's model category of weak N categories, or it could be any of the ones I mentioned before, Thompson-Mani, Siegel, whatever. So once we have this model structure on K operads, so we're going to transfer this up to out K, then the next step, if we can do this transfer, is going to be to localize it. So we want to find a way to localize it so we can make this thing act homotopically invertibly. So I have to tell you a bit about localization. And we use the machinery from fundamental localizers, which were invented by Grothendieck, and their theory was worked out nicely by Szynski. So I'll tell you what a fundamental localizer is, and then we'll be doing a localization with respect to a fundamental localizer. So a fundamental localizer is a class of functors between small categories that could possibly be the weak equivalences of a model structure. So it has to have all the identities, closed out of the 2 out of 3 property, closed under retracts. These are things that you would expect of a collection of weak equivalences. If you didn't have these things, it's not a good collection of weak equivalences. It has to have the property that if I have a category that has a terminal object, then the functor from that category to the terminal category is one of these. So that's sort of like saying, if your category is a terminal object, it should be null homotopic. It should be equivalent to a trivial thing. It also has a version of Quillen's theorem A, which says that basically if I want to check that a given functor is in my collection of weak equivalences, it's enough to check it on these slice categories. So if you have those properties, then that's what it means to be a fundamental localizer. And we'll call the elements of W equivalences. They seem like potentially a category of weak equivalences. And then it's a theorem, well, it's coming on this slide, that these things exist. So that the localizations exist with respect to these things. W aspherical is going to mean that that the small category looks like it's null homotopic from the eyes of W. So the unique functor to the terminal category is actually in W. Then this category, it might not be terminal. It's not an isomorphism. It's just that it's going to be homotopically equivalent to the terminal thing. So that's like being null homotopic. And we say that a localizer is a proper fundamental localizer if it's generated by a set in a suitable way. So that means that this class of functors is minimal with respect to making the elements of S aspherical. So I'm gonna start with a set of small categories, and I'm gonna invert them all homotopically. I'm gonna nullify to make them all weakly equivalent to the terminal category. But that's gonna also invert some other stuff, and whatever it generates, that smallest collection of things that it inverts, that's my W. So that's what it means to be proper. It's generated by a set like this. For example, let's do some examples. So I can look at the collection of functors whose nerve is a weak equivalence. That should be like a collection of weak equivalences. And indeed, this satisfies the four axioms on the previous slide. Szynski proved that. And actually, this one is the minimal fundamental localizer. So it's generated by the smallest possible information. In fact, I think I read this. Yeah, it's the localizer generated by any single category A with a terminal object. So take any category with a terminal object and say, you know what? That thing is boring. That should be null homotopic. That's going to actually nullify all the categories with the terminal object and maybe some other stuff. And exactly what it's going to do is it's going to make it so that any functor whose nerve is a weak equivalence ends up in this collection W. So that's one example. Another example is truncation. So if we hand it the category that looks like the n+1 sphere, so that's a category with the homotopy type of the n+1 sphere, and we nullify that, then actually the new equivalences are exactly the n equivalences, things that are an isomorphism on homotopy groups less than or equal to n. That's important. Remember that came up on an earlier slide. We're going to need that to make this thing here equivalent equivalence. And for example, if I take n equals 0 here, then W0 is a potential class of weak equivalences. These are the ones that induce an isomorphism on connected components. And to be W aspherical means it should be null homotopic from this point of view, so those are connected categories. Those look like the terminal category from the point of view of connected components. Yeah?
The homotopy type of the n+1 sphere in which model structure?
No, just so spaces. Spaces. Like, so if I have a category, I can always get to a space, right?
Yeah, with the nerve.
Yeah, exactly. So that I want it. So if that space has the homotopy type of an n, so weak homotopy type.
Yeah.
So the same homotopy groups as the n+1 sphere.
Is the Sn+1 sphere in the image of the nerve?
No, I'm saying I take there exists a category such that if I take its nerve, then it's homotopy equivalent to the n+1 sphere. Yeah.
Okay. Yeah. Okay.
And that's the one I want to invert. No problem. I'm certainly happy to answer questions by all means, because it's a crap load of information. Please ask questions if you have them. I wanted to give another example, and this is actually, remember at the beginning I said there's this stable line, and the theorem at the end of the day should be that that this is equivalence, but not for all n and k, but only for some specific relationship between n and k below that stability line. So where does that line come up in our proof? It comes up in the fact that the comparison between this QK collection, the category of collections for k operads, and the category of symmetric collections, that this is actually an n equivalence in that stable range. And that comes down to a classifying space calculation. So the point is going to be that in that stable range, we're going to have equivalent equivalences here, but only after a suitable localization. We're going to have to localize both of these categories of pre-sheaves. And then we'll have equivalent equivalents here that we can lift equivalent equivalences there. So we'll get there. Okay, so that's why by Dolan stabilization, our theorem needs n+1 less than or equal to k, which is good, because if our theorem just proved in general that for any n and k you had this equivalent equivalence, the theorem would be wrong, because we know that the stability happens after the stable line. By the way, for n equals 2, there's this special case, which is the connection of braided operads. So our theorems always have two cases. One is for k bigger than or equal to 3, and the other one is for k equal to 2. So yeah, the k equal to 2 case is always separate, because the comparison there doesn't go to symmetric operads, it goes to braided operads. Cool. And by the way, of all of these localizers I just gave you, they each have a homotopy theory. So for example, the homotopy theory that I get from the minimal fundamental localizer is exactly the same as the homotopy theory of spaces. And from the WN localizer, it's n truncated homotopy types. And that, yeah. Cool. So now we have an idea. We have a way that we can localize pre-sheaves, and then we'll have to have a machine for lifting localization. So the way that we're going to localize pre-sheaves is I'm going to start with a model category and a small category. I'm going to look at the category of pre-sheaves, and I want to localize with respect to the level-wise weak equivalences in V. So that means that's a class of weak equivalences I can localize with respect to. The idea is that I'm going to get what are called locally constant pre-sheaves. So I'll define that. A pre-sheaf is locally constant if for every WA spherical small category, so these are the ones that look like they're null homotopic from the point of view of W, so they look like null homotopic, then my A is locally constant if for any map between them, the corresponding pre-sheaf is isomorphic to a constant pre-sheaf in the homotopy category. In other words, my A is locally constant if it looks like an A prime, which is WA spherical, so those are the ones that look like constant ones in the homotopy category. So locally constant pre-sheaves, we're going to denote them in this way, and I'm about to give you a model structure for them, but let's do an example. So if we take this minimal fundamental localizer, then for a pre-sheaf to be locally constant means that for any map in A, the pre-sheaf takes that map to a weak equivalence. Okay, so I started with pre-sheaves into a model category. Any morphism in A goes to a weak equivalence. Okay, those are reasonable objects. You might want to say that those objects are, so those will be the local objects of this new homotopy theory. We're focusing attention on these local objects. And by the way, the reason for that is because this W infinity is generated by any category with the terminal object, including this walking arrow. So that means that I'm going to nullify exactly with respect to all of these things. So I'll invert all of those arrows. Okay. Yeah, and then a functor is a local equivalence if it induces an equivalence of categories on the locally constant ones. So this is the usual way that we do localization in every setting. You start with the things that you want to invert, W. Then you say, hey, what objects, what objects see this W as if it was weak equivalences? Those are my local objects. And then I say, okay, now I've got my local objects. What else do they see as if they're weak equivalences? Those are my local equivalences. So it's kind of a double orthogonality thing. But the point is, this is going to be the smallest collection of weak equivalences that could possibly be sort of permissible as a collection of weak equivalences for a homotopy theory, which is generated by what I started with. That's the idea of this. That's the point of this. Okay, so time to give you some theorems, and I want to check my time. Okay. We proved that. Yeah, see, this answers, what was your first name? Raphael's question. You can take the category of pre-sheaves, and for any proper fundamental localizer, you can invert it. You can take W locally constant pre-sheaves for any such W. So it doesn't have to be W infinity. On the previous slide, this was an example for W infinity, but you can do it for Wn or for any localizer. And you can start with any of these three model structures, projective, injective, or reedy. So that gives me a local model structure on presheaves, and the fibrant objects are exactly the locally constant presheaves. Furthermore, I can induce Quillen equivalences between these local model structures. If I have a local W equivalence between indexing categories, then I get a Quillen equivalence. And that's going to matter because I am going to have a local equivalence between this QK and this sigma. So that means that I'm going to get a corresponding equivalence between the local model structures on presheaves. I don't want to, there's a reference at the end, a paper I wrote with Boris Chorny, which can be seen as a kind of a generalization of this whole story. But instead of being about functors from a small category to a model category, it's about functors between two model categories and putting a model structure on those functors. But there's set theoretical abstraction, so we take the category of small functors between two combinatorial model categories, and we do the same kind of thing as this. Okay, so let's talk about left Bousfield localization in general, because this told us, what we just did, told us how to construct these localizations on the level of presheaves, but to construct a localization on the level of k-opereds, that's not a category of presheaves, so we need to do a different way of doing localization there, and the answer for that is going to be left Bousfield localization. We can put a model structure on the category of k-opereds using that general transfer machine I told you, and then we want to localize that model structure. So what we're looking for is a new model structure such that some given collection of morphisms are weak equivalences, and this model structure is universal with respect to the property that the identity functor is a left Quillen functor. So it's the same category, but it has more weak equivalences. The same double orthogonality here. A C local object is one that views these morphisms as if they were weak equivalences according to simplicial mapping spaces, or homotopy function complexes, better to say. And a local equivalence is one that looks like a weak equivalence from the point of view of all of these local objects. The same double orthogonality. And so our goal is going to be to lift this localization. We had a way to localize from QK to B. That's a presheaf category. We just showed you how to localize that and get this locally constant presheaf. And then we want to lift that up to, we want to lift that localization to a localization of k-opereds. But there's a problem. This category of k-opereds is not actually known to be left proper. In fact, there are counterexamples. Depending on the base V, it's not left proper. So if you wanted to do left Bousfield localization in the normal kind of homotopy theoretic sense, you need to start with a model category that's left proper. So this is a big problem. For many, many years, and I'm going to show you in a minute a slide that has, I think, 9 examples of times that people wanted to do left Bousfield localization, but they didn't have a left proper model category. Well, we have an answer for that. The answer is these semi-model categories that I alluded to earlier. So I'm going to show you a theorem. It's in our other paper, which is called left Bousfield localization without left properties. So we finally solved this old problem of how do you do it, and we get localizations in all those contexts. So what is a semi-model category? It's like a model category, so it has weak equivalences, cofibrations, and fibrations, but I only know that trivial cofibrations lift against fibrations if the domain of the trivial cofibration is cofibrant, and I only know that a given map factors in this way if the domain of that map is cofibrant. So this is exactly the structure you get when you try to do that transfer theorem, but you can only analyze it for cofibrant objects. You only have nice behavior for cofibrant objects. However, so you still always have the other factorization. In particular, if I have like a map from the initial object to any x, I can always factor that as a cofibration followed by a trivial fibration. There's no restriction on this factorization. Hence, I still have cofibrant replacement, which means I can take, if I have some collection that I'm working with, I can cofibrantly replace everything in it, and then On that new collection where I cofibrant replaced everything, I have all the model category axioms because every object is cofibrant, so there is no restriction. This only holds for cofibrant objects, but if all the objects are cofibrant, there's no restriction. In particular, take any model category result that you like, and there's an analog for semi-model categories. So these analogs appear in many of my papers. One that I recently proved in the paper with Michael was that if you have a combinatorial semi-model category, so that means it's on a locally presentable category, and it's cofibrantly generated, then it's equivalent to a combinatorial model category. So the homotopy theory of these things with this small restriction is exactly the same as the homotopy theory of full model categories. And in practice, they're just as good as a full model category because you can do all your favorite constructions. Now, what is left properness? I said this thing is not left proper. Left properness is like the gluing property in spaces. It means if I have a weak equivalence and I glue on a new cell by a cofibration, the resulting thing should still be a weak equivalence. When you have left properness, you have the following upside. You have two upsides. One is that if you have a lifting problem of a cofibration against a fibration, now normally you don't have a lift here. I mean, one of them would have to be trivial. But if you take the cofibrant replacement of this, and if you're able to construct a lift here, then you get a lift there. And this is the crucial thing in Hirschhorn's book that allows them to do left Bousfield localization. That's why they need left properness. However, I just want to point out that for a semi-model category, you would never be in the position of trying to do this lift for random A and B. You would only be in this position when A was already cofibrant. Therefore, you wouldn't have to do a cofibrant replacement of it. Similarly, look at the left properness condition. In a semi-model category, you wouldn't ask for this. This is the wrong thing to ask for. You would say, suppose I have a weak equivalence between cofibrant objects, and I push it out along a cofibration. Is it still a weak equivalence? And that's actually always true. So the point is, in a semi-model category, both of these things are automatic. It's as if every semi-model category is already left proper. So you can do the localization machine in the semi-model category context. The result will only be a semi-model, but I just told you they're just as good as model categories. And so that's a nice way to handle the situation where you don't have left properness.
Is the category of cofibrant objects a model category, a semi-model category?
No, it would be the opposite way around. It would be that if I took a semi-model category and I restrict it to cofibrant objects, it's going to behave exactly like a model category. But it isn't literally a model category just because of like limits and colimits, right? If I take a limit of a bunch of cofibrant objects, there's no reason it would be cofibrant. But it acts like a model category, yeah.
Okay. So the other way around is not true.
No, if you have a model category, you already have all the axioms.
Yeah, but still, if I can just consider the category of cofibrant objects in there instead of semi-model.
It would actually act like a full model category. I mean, it would have all the model category axioms.
Well,
It's a cofibration category, I guess. So
yeah.
So okay, if you have a model category and you focus on the cofibrant objects, if you have a semi-model category and you focus on the cofibrant object, they will behave exactly the same. That's the point. Okay. I mean, the point is semi are generalizations of model categories. I couldn't get them from a model category. Might have to go a little faster. So we have a general theorem that does localization. We want to do left Bousfield localization without left properness. The trick is always this kind of Jeff Smith style theorem. So the Jeff Smith theorem is a way to start with a locally presentable category, some collection of maps that you want to be the weak equivalences. For us, those would be the local equivalences, and some set of maps I that are going to generate the cofibrations. And then you do some, they have to satisfy some conditions that make them permissible to be the collection of weak equivalences of a model category and the generating cofibrations. And then the upside is that by the magic of locally presentable and accessible categories, there exists a set J that generates the trivial cofibrations and makes the whole thing a model structure. So what we did was we did a semi-model category version of this, but then we have some weaker conditions to check. So we have easier conditions to check, and the result is a semi-model structure. And then the corollary of it is that if you start with a combinatorial semi-model structure and some maps that you want to invert and no left properness at all, then you're going to get a semi-model structure on the local one. So with those the new weak equivalences as the local the weak equivalences are the local equivalences, And furthermore, this thing satisfies the universal property that you would expect. In particular, by the way, if you start with a combinatorial full model category, but without left properness, you can localize and you still get a semi-model category. So there were many, many, many examples in the literature where people wanted to localize, but they couldn't prove left properness. Voevodsky has a great example where actually he proved his thing wasn't left proper and then proved that the localization doesn't exist as a model structure, but we prove it does exist as a semi-model structure. And there were a bunch of other examples. And I put more here because I always wonder if my audience has even more examples that they know about where somebody wanted to localize but didn't have left properness. If so, please tell me, and I'll add more examples to the paper, but the paper is already half examples. Yeah. So in all those cases, we now have a semi-model structure. Now let's finish our Bayes-Dolan thing. So I have I'm going to take a nice symmetric monoidal combinatorial model category, and I have a substitute. Now it could be the substitute for k-operads, or for symmetric operads, or for braided operads. Doesn't matter. The projective semi-model structure on this category of operads exists, so the transfer works. The transfer theorem works. And I can localize it for any proper fundamental localizer. So I can do this localization here using our semi-model localization theorem. And by the way, that localized thing coincides with what I would get from transferring. So if I started down here and I wanted to get to the local algebras, I can either go to algebras first, then localize, or localize first, then go to algebras, and it's the same thing. That was another paper Michael and I published in HHA, the fact that these two ways of going around are the same, and that's also on the references on the last slide. So when we do all this with the localizer W infinity, we get back the higher braided operads that we talked about before. But the point now is that you can actually do it for other fundamental localizers as well, and you can do, for instance, truncations. But even just getting it for higher braided operads, we're getting a semi-model category version of stuff that Michael Vatanen only was able to prove previously on the homotopy category. So that's already nice. All right, so finally we have all the pieces in place. Everything on the board is defined. We know what we need. This is a semi-model category that I get by localizing k-operads to force these things to act invertibly. So these are this is my model structure for higher braided operads or for locally constant operads. Same thing here. This is the usual model structure for symmetric operads. And the last bit that I need to know is I have these equivalent equivalences down here by classifying space computation, so I want to lift those up to equivalent equivalences here. Oh yeah, here's our plan. So we want to lift this equivalent equivalence to this equivalent equivalence up here, but it turns out to be much easier to lift the outer one to equivalent equivalence with symmetric operads and then just use the 2 out of 3 property. Both of these things will be equivalent equivalent to symmetric operads, so then my 2 out of 3 is equivalent equivalent to each other. So how do you lift equivalent equivalences? Well, if you ask a category theorist and you say I've got a square of adjoint functors, like say this square right here, a square of adjoint functors, and I have an equivalence downstairs and I want to lift it, they're going to tell you to go look at Beck-Chevalier. So maybe there should be a homotopical version of that, but we couldn't find it anywhere in the literature. I think nobody ever worked it out, remarkably, because it's a really basic result in category theory. So we did that. It's in our paper. A square is called homotopically Beck-Chevalier if the 2 ways of going around yield an isomorphism in the homotopy category. And we know when that occurs. We give a condition to check, which we are able to check in the relevant case here. And then the upshot is that if I have equivalent equivalence downstairs, then I get equivalent equivalence upstairs. So that's how we lift equivalent equivalences. It's a homotopical version of Beck-Chevalier. In particular, we do it for substitutes. And now I've only got a couple minutes left, so I can state the various Bayes-Dolan theorems. So we're going to start with a combinatorial symmetric monoidal model category with cofibrant unit. We need the cofibrant unit for this last bit, the lifting bit. All of the categories I started with at the beginning, so Resk's model of weekend categories, Thompsomani, Ara, Bergner-Resk, Siegel, all of these things, Simpson, they satisfy these conditions. And the good news is that in that case, then I get a left equivalence between the localized version of k operads and the localized version of k plus 1 operads, or indeed m operads for any m bigger than k. So it takes whatever stabilization you want. You get these equivalent equivalences. And for the case of k equals 2, you have to use braided operads, but you have equivalent equivalence to braided operads, so that's good. That's what you wanted. In particular, plug in any of these models here for V, and you have the Bias-Dolan stabilization theorem in any of these models of weak n categories. So this solves in a strong way what Bias-Dolan we're asking for. Now, I will say, and I think it's on a later slide, this is not a complete list of every possible collection of weak n categories. There are some notable ones that are left off. The ones that are left off are exactly the ones that don't have a known monoidal structure. So without a monoidal model structure, we can't do the symmetric operand thing, so we can't make this theorem work. So our theorem will apply in those other models, like I think Barwick has a model of n-fold complete Siegel spaces. We would apply there after somebody finds an appropriate monoidal structure. Okay. So that's the main theorem there. And then one upside is that if the category V that you start with is actually already truncated, then you don't have to truncate it at the level of k operads. So you have a more direct comparison just with symmetric operads already. So in other words, this works with the minimal fundamental localizer. In the previous one, we needed the WN localizer, so that's bigger than the minimal one. The minimal one is going to give you locally constant Cauchys. The WN one also does truncation, but if the thing you started with is already n truncated, meaning all the function complexes are local, are n types, then it's enough to do the minimal fundamental localizer. So that's nice. And when you do the minimal fundamental localizer, we know that this is the category of higher braided operads. So we have a stabilization theorem for higher braided operads. Those things stabilize as well. For example, Resk's model of weak n categories is n truncated. That's easy enough to check if you read Resk's paper or we check it in our paper. Or you can take any of these other models and you just have to apply the truncation of them, which is itself a left Gaussian localization. And it doesn't matter if these things are left prop or not, because I can do left Gaussian localization even without left properness. So this machine works in any of the models that you like if you truncate them. And then truncation is sort of natural here because you have to go, a lot of these are modeled, like Resk thing is also a model for infinity n categories, but if you truncate, then you get weak n categories. So that's why truncation is kind of natural to do here. And then lastly, we can go back to the way that Michael proved Bias-Dolan stabilization in 2017. So he had a version where it's encoded by a specific k operand. In other words, k tuply monoidal n categories are algebras over this GK, and k plus 1 tuply monoidal are algebras over this thing, and you get equivalent equivalence between those categories of algebras. That's a corollary of our general theorem here. If you can do it for k operads and k plus 1 operads, then you get it for the way that we had in 2017. Lastly, you can also do this for, instead of weak n categories, you can do it for n plus m comma n categories. So I'll show you that in just a second. But yeah, this version of stabilization works for all the models that we've done. In particular, it works for n plus m comma n categories in this way. So there's a stronger stabilization result that works for things that are a little bit different from weak n categories. And the last point I wanted to make is that it holds for all the models that we know that have a monoidal model structure, and it will hold for other models if somebody finds a monoidal product for them. These things are combinatorial model categories. They have cofibrant. Well, they don't have a monoidal structure, so you have to find a monoidal structure and then prove the unit is cofibrant. Then you could use our theorem to get all of these stabilization results automatically. So that's it. That's what I wanted to tell you. The The paper that I just told you all about is this one. So here it is on archive. It'll appear soon in the transactions. The left Gauss field localization without left properness is on archive. The paper that did the 2 ways of going around was published in HHA there. And then I think I mentioned the paper with Boris Chorny. And then there's a lot of papers that are more foundational in this subject that are maybe also worth checking out. So all of the slides are on the webpage. I know it's pretty fast to go through it, but yeah, if you want to read these papers, hopefully this gives you a roadmap, and I'm always happy to answer questions either now or by email. So thanks for your attention.
Any comments or questions? Thanks very much, by the way. It's very interesting. Any comments or questions?
Yeah, so the last question I had, indeed, you were right. I mean, the other way around.
Yeah.
So the question would be, there's this result, right, when that every combinatorial model structure gives you a right proper model structure by restricting to its algebraically hybrid objects.
Oh, yeah.
This is Nicolas.
Yeah.
Would it be like, so it sounds like maybe there's a chance that the same model structure gives you an actual model structure by restricting to its algebraically co-hybrid objects.
Yeah, so that is true, and we proved that. So some time ago, long time ago on the slides, I mentioned that every combinatorial model category is equivalent. Every combinatorial semi-model category is equivalent as a semi-model category to a combinatorial model category. So there are 2 ways to prove that. One way is to do the Girard theorem kind of thing. So you start with a combinatorial semi-model category. In particular, it's a locally presentable category. I can embed it into the category of simplicial presheaves. Then I can take a localization of simplicial presheaves to get an equivalent homotopy theory. So this was like Dan Duggar did this, and that works. So we prove it. And I believe, I have to check, but in the paper on left Gauss field localization without left properness, I know I also considered exactly what you just said, the algebraically cohybrid objects. I think that one works as well, but I'm not sure if I spelled it out or if I just left it as a remark. But indeed, yeah, the idea is if I'm in a semi-model category and I want to make it a model category, I have to somehow restrict down to the cohybrid objects, and that's another way to do it, which is in isolate. I believe that theorem has an extra condition, though. Do you need it to be simplicial?
I mean,
So
they have to be combinatorial model structures equivalent after all to a simplicial one.
Well,
Right?
but then I'm doing this. I mean, then I'm already getting it. If I to replace my semi-model category with a simplicial one, it's already a combinatorial simplicial one.
If you do it, yeah, the way, yeah.
But I think that if it was, I think I proved that if it was, whatever the conditions are of the Ching and real, whatever the conditions of Ching and real, I believe that if they're satisfied in the semi-model way, then when I go to the algebraically cohybrid objects, I get a full model structure. I think it's true, and I think I proved it, and I think it's probably in this paper. If it's not in this paper, it's in some random note that I wrote in my computer.
Simon and Henri and I have a paper where we did a recent paper where we did these things as well and got rid of most of these conditions, like the Ching and real ones, by using a different approach.
Oh, wow. Okay, so we have to talk even
Yeah,
more.
we're glad to talk about that. And we did it for the Fibrant case as well.
Model categories there, or
We have what, sorry?
weak model categories?
Yeah,
there?
so we do it more, so weak model categories are sort of more general than left semi-model or right semi-model. I think that was Simon's motivation for introducing them. So that's our basic framework, but then we have lots of theorems about what happens if you have an actual semi-model category.
And it's certainly worth advertising this work of Simon Henry, both because it's great work and because he was a postdoc here, but he also has a way to do left Gauss field localization in the context of these weak things. So I think that you would also have a theorem similar to this one, somehow, that if you have some locally presentable weak thing, and then you want to localize it, you get a weak thing without left properness.
Right.
So that should be some sort of related result to this that's worth advertising.
Also, vaguely remember a few years ago I read a note or a paper by Hirschhorn who did something like that.
Oh, really?
Yeah.
So there was in this paper by Goers and Hopkins, they knew how to, they focused on the category of algebras over some operad, which is in general not left proper, and they did a left Gauss field localization of it. in that specific case. And they said, we learned it from Hirschhorn. So I wouldn't be surprised if Hirschhorn sort of wrote up his thing. I don't remember reading it. However, another guy very recently, I think his name is Carmona, Victor Carmona, he is a student of Fernando Moreau. He recently did a version of this theorem exactly like what we did, following our paper, but for cellular. So this is more of what Hirschhorn would do. I doubt that Hirschhorn would do the combinatorial case because he was the cellular one. So yeah, it's true as well for cellular. Although, of course, the proof is different. I mean, you can't use the Jeff Smith magic because you don't have local presentability. But yeah, maybe later you can show me this Hirschhorn.
Yeah, I'll have to look it up. If I find it, I'll.
Yeah, thank you.
Any more comments or questions? Well, if not, then let's thank David again. So that's it for today, and then next week we have Charles Walker. We'll be talking. So, thank you.
You are leaving immediately or not?
Well, I can chat for a few minutes.
No, but because